This is a thought experiment capturing point charges inside of a unit sphere. This wouldn't happen this simply in nature, but it's an interesting exploration of complexity that comes from simple interactions. When you add another identical charge, Coulomb's law says that these will repel each other with the strength of repulsion falling off with the square of the distance. This is often referred to as an inverse square law, and the same fall-off shows up in other laws of physics. As more points are added, the interaction of each pair of points needs to be considered. So there are many repulsion vectors. To get the total force at any given point, the individual forces need to be stacked or added to produce a single total force vector. This repulsion vector can be broken down into two pieces: the part that goes straight out of the sphere, called the perpendicular vector, and the part that goes along the outside of the sphere, called the tangent vector. When the simulation is running at full speed, the stabilization is too quick to really see the tangent vector. If I pause the simulation, we can catch points while they are still moving. The perpendicular vector isn't important to the simulation because the point can't move out from the sphere. But the tangent vector tells us which direction to move the point. Analogy is if this was gravity, the tangent would be pointing downhill. And as we all know, if you keep going downhill, you eventually get to where every direction is uphill. This is a stable place for the point. If I resume the simulation, you see the points move and the tangent vectors shrink to zero as the points reach the stable position. By connecting the points, I can create polyhedra and show information about how far apart the points are. You might think that if all the points were repelling each other equally, that all the points would be the same distance apart. But except for a few special cases, it's impossible for them to all be the same distance. See here, this is 1.4142 and 1.7321. So the equal distribution can only happen for tetrahedrons, octahedrons, which are 6 points, and an icosahedron, which is 12 points. Everything else requires different distances for a stable distribution. An interesting question is, how are those different distances distributed? By giving each unique length a different color, it becomes easy to see the distribution of those different lengths. So as we see with a tetrahedron, they're all the same length, but when we start having 5 points, there's 2 different lengths. Now the rest of the video is just an exploration of the different symmetries that occur going up to 32 points. So here with 5, you end up with a triangular symmetry, and then as we increase, so this is the octahedron we were talking about. This is one of the other cases where everything can be the same, 6 points, and then 7 points. Some of these configurations stabilize more quickly than others. Here we see a 5-fold symmetry with an north and south being equal. With 8 points, we have a 4-fold symmetry. This is what's called retroreflective symmetry, where the top and bottom are twisted relative to each other. But it's a square symmetry, 4-fold symmetry, or it's called a 4-fold retroreflective symmetry because the top and bottom halves are the same except for being twisted. 9 points. Here we have a 3-fold symmetry. So you can see the triangular there, and then but it's the same from top to bottom. And then 10 points. We've got another one that's retroreflective, 4-fold retroreflective. 11 points. So this one is unique in that there's not the top and bottom do not reflect each other. So we have symmetry from the left and right, or from top to bottom, how you want to say it. but the rotation, but the top and bottom don't match. So you have this. So there's less symmetry here than in many cases. I don't know how related it is to 11 being a prime number, but now 12 points. This is the last of the ones that can actually have all the same size. This is called an icosahedron. 13 points is another one of these cases that where it's reflective around in two directions, but not in the axis. So it's got a limited symmetry. Another one with a really odd number of points. 14 points. Here we have a retroreflective six-fold symmetry. So nice equator. Now these colors are not for specific lengths, but for relative lengths. So these are all the same because these are all the same color because they're the same length, and then these are all the same color because they're the same length, and so on. 15 points. So this is symmetric. This looks a little retroreflective, but I'm not sure what it's called when there's actually not an even. It's just a slight twist. It's not a full halfway twist between the two. The 16 points, this is a tetrahedral symmetry. So there's four triangles there. They're not opposite each other. Instead, they're in the form of a tetrahedron. So there's another five-fold symmetry. And here's another one with a retroreflective square symmetry. "19 points. It's another odd one where the symmetry is clearly there. This one takes a little while to stabilize, but the symmetry is actually much harder to see. So this is a triangular symmetry with axial top and bottom being the same. So this okay, finally stabilized. Okay, this one took a while to stabilize, but you can see that there's symmetry there from going around, but there's not symmetry top to bottom, depending on how you want to think about it. 22. This is another one with tetrahedral symmetry. You can see the four triangles there, but it's just a few different colors, different lengths that exist. So this is a threefold retroreflective symmetry. So you can see these are cross each other, the orange, purple and purple, yellow and yellow. 24 points. This is a cube symmetry. So there's 6 sides to it. But it's in a cube format, but it's twisted. I'm not sure if this is a form of retroreflectivity or not. I don't think 25 is going to stabilize in any reasonable time. So this is a five-fold symmetry. And this is another one with tetrahedral. It doesn't show up as a triangle, but you can see that the 4 different places that this set of purple and cyan rods are. So there's a threefold symmetry, though there's actually a slight twist to it, and you can see that it's not symmetric. So this is they're the same sequence, but they're out of phase with each other. So things are slightly skewed with each other. It's not really threefold. And 32 has a nice dodecahedral symmetry. There's 12 of these pentagons, but their pentagons are broken up. So this is a 60-sided shape. That's the end of my little show and tell. Hopefully I can make something more interactive available in the future.